Hello Math 1093, this video is called Shift and Stretch for reasons that I think will become apparent pretty quickly. In this video, I've produced already the graph of a function f of x. Now f of x is a special function. It is the absolute value function, except I've defined it only on the interval from -1 to 2, including the endpoints. That's why that graph here stops at the point -1, 1 and 2, 2. Because I've only defined f on a restricted domain for reasons of illustrating a certain idea more than anything else. In this video, we're going to talk about what that graph has to do with the graphs of these other two related functions. They're related because G and H are both defined in terms of f. So what we're going to do in this video is we're going to graph each of these functions and talk about what these graphs have to do with the original one. Alright, so let's start with g of x. So the way I'm going to approach this is I'm going to build a table of values for x, f of x, and g of x. Because really my main conduit for understanding g of x is to think about f of x. This is related to f of x. Alright, so let's pick a few reasonable test values for x. Let's use -1, 0, 1, and 2. Alright, now I could just go through and go ahead and write down the values of f of x here. I mean, I could go ahead and fill this out, but I actually want to step through this one input by one input for g of x, so I can think about how the values of g of x are related to the values of f of x. Alright, so let's begin with -1. Let's pick a different color here. There we go. Alright, so when x is -1, I want to figure out what is g of x. Well, g of x, this is equal to, I'm just going to turn that into an equal sign there. G of x is equal to 2 times f of x. So in order to figure out the value of g of -1, I need to figure out what f of -1 is and then multiply that by 2. Well, according to this graph, f of -1 is 1. So f of -1 is 1. That means g of x is twice that. G of x is 2 when x is -1. So that means that I'm going to have a point on my graph right there at -1, 2. Alright, when x is 0, what is g of x? G of x is twice f of x, and f of 0, according to this graph, is 0. So g of 0 is going to be twice that, which is 2 times 0, that's just 0. Alright, what about g of 1? G of 1 is going to be twice f of 1. F of 1, according to this graph, seems to be 1. So that means g of 1 is going to be twice that, that's 2. Alright, I need to record these points in my graph here, so that there's 0, 0, there's 1, 2. And finally, what is g of 2? Well, g of 2 is going to be 2 times f of 2. F of 2 was 2, so g of 2 is going to be 2 times that, which is 4. Now, 4 points don't prove anything, but I think that if I were to go through and imagine taking other values of x, and imagine each value of g being twice the corresponding value of f, here's what I would see. I'm actually going to go ahead and sketch the graph of f of x in here, so it's visible. Okay, so there's a little bit of it, and then here's the rest of it. Okay, now again, that was the graph of f, not the graph of g. But at any given point, the value of g is going to be twice the value of f, so it's going to be twice as far away from the x-axis. So I'd have a point here, I've got a point here. Sorry, I realize those are not visible, but I also have points here. Those are all twice as far from the horizontal axis as the corresponding points on the graph of f. And before I know it, I've got what I think is a pretty convincing graph of g of x here. Sorry, that should be straight line segments. It shouldn't be all over the place. I'm just trying to mark over what it did there. Okay, so that right there is the graph of g of x, or sometimes people will call it the graph of y equals g of x. And you'll notice that this multiplication by a factor of 2 here, what it ends up doing is it stretches the graph of f vertically by a factor of 2 from the x-axis. I say from the x-axis because there's a lot of ways we could stretch something vertically. Like if I were to choose a different center line for the stretching, I might end up much further away from the x-axis. So all I'm saying is that the x-axis is going to remain fixed here. That's why this point here remained fixed, the origin, and then everything else becomes twice as far from the x-axis as the graph of f. Alright, now let's talk about h of x. Alright, so I'm going to move over here, give myself a bit more room to work. Let's draw a new set of axes. There we go. Again, each hash mark is 1 unit. Alright, so there's 1 and 2 there, there's 1 and 2 there. This is the x-axis, and this is going to be the h of x axis. Alright, so this time I'm talking about the function h of x equals f of x minus 1. And we're going to investigate what this does to the graph of h as compared to the graph of f. Again, just for comparison's sake, let's go ahead and put the graph of f in here. That graph looked like this. There we go. So that was the graph of f of x as a function of x. So now we're going to work on the graph of h of x. Again, going to do a table of values here. By the way, anytime you're curious what a certain algebraic transformation is going to do to the graph of a function, a table of values is always, at least I think it's always, a good way of investigating that. So just as a reminder, h of x is equal to f of x minus 1. I'm going to use the same test values as earlier, negative 1, 0, 1, and 2. And again, we're going to step through these carefully to see what's happening with the value of h at each point. All right, so what is h of negative 1? Well, h of negative 1 is going to be the same thing as the value of f of negative 1 minus 1. So f of negative 1 was 1. So h of x is going to be that minus 1, which is 0. All right. When x is 0, h of 0 is going to be f of 0 minus 1. f of 0 was 0. So h of 0 is going to be that minus 1. That's negative 1. Similarly, f of 1 is 1. So h of 1 is going to be that minus 1. That's 0. And finally, let's make sure I got that point there. Okay. And finally, f of 2 was equal to 2. So h of 2 is going to be that minus 1. That's 1. So I believe if I connect these points, I will probably have the correct graph of h. In fact, I'm going to go and fill those in. Alright, so how do I know I can fill the graph in this way? I have the 4 points, but why can I fill those in? It's because at any point, this point, for example, on the graph of h is going to be the same as this corresponding point on the graph of f, but shifted down by 1 unit. So everything here is shifted down by 1 unit on the vertical axis from the graph of f. Okay, I've sort of cluttered up the graph by doing that, but I think you get the idea that the new graph, the graph of h, is the same as the graph of f, but shifted down 1 unit. So this is a shift down by 1 unit. Okay, you could also imagine that had I added 1 here rather than subtracting 1, I would have ended up shifting upward by 1 unit. Okay, so these are just a couple of examples, and you can find more comprehensive guides on the internet to how algebraic transformations end up transforming the graph. This is meant to be a review more than anything, but we're going to use these ideas as we talk about trig functions. For example, pretty soon we're going to know what the graph of this function looks like, f of t equals sine of t. We're going to talk about that in class. But we might wonder, okay, well, what does the graph of something like this look like? 3 times sine of t, or perhaps h of t equals sine of t minus 5. So the goal of this video was to help us answer those questions by thinking about how the graph of this function might be related to the graph of this function. I realized these were not trig functions, these were absolute value functions, but the principle is the same. If I write down this function, its graph is going to be the same as the graph of f, except it's going to be stretched by a factor of 3 away from the horizontal axis. And the graph of h would be the same as the graph of f, except shifted down by 5 units. So the principles work the same, even if we're working with a totally different type of function.